post it later. Okay. All right. There we go. Oh, no, let's do this one. That's not the one I wanted. Let me actually minimize this. Minimize, 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 minimize. This There we go. Okay. All right. Have you done an algorithms class before? Or data structures with who? Oh, she's teaching data structure? Oh, wow. Okay.
I think the old teacher like some because I was taking the one on separate.
Mm-hmm.
CS1 and because there like some sort of issue with like like the teacher would know just CS2 it's like couldn't teach like wasn't anymore.
Oh, wow.
So we
Okay.
just like spam what it wants to teach it. And
Fine. Okay. How do you like CS1? What's that great?
it was that was fun.
Okay. Did you know anything like code like how to use Python? Oh, okay. Okay. I see, yeah. I heard for like some people have like mixed opinions on it.
Like never done coding before. It's
Yeah.
impossible.
Yeah.
Just what I have no idea.
So for those people. Yeah. Yeah, that's kind of the boat I was in. But actually, yeah. Yeah. Okay. Let's get going now. I don't think anybody's gonna show up for a while. So actually let me switch this off for now. Let's just go to like let's just run through like a simple algorithm. This is for like graph stuff. So stop that marker. Sorry. Yeah, okay. I'm gonna go to another one. Ruben, that's Nick. Nick Ruben. All right, today we're going to be going over the algorithm that we use in graphs called DFS, depth first search. Uh, this is kind of one that a lot of companies like to ask just because it's fundamental, but specifically Google. In fact, I actually got a question on this from Google, and I didn't sign an NDA, so I think I'm okay to like disclose this. But like, let's say you have like, I guess like first of all, like, does everybody know like what a graph is per se? Like, what does a graph consist of?
Just like nodes that have like attached to other nodes.
Yeah, exactly. So like, let's say I know like you guys might have like encountered like graphs and like various other things. I know like maybe you haven't gotten to this yet, but in data structures, there's like a binary tree. You can think of that as like a graph where like you have like a node and then it points to another node somewhere else.
Like a file system.
Sort of, yeah, you can think about it like that. Actually, that's a good point. It's like you know when you're using like terminal or something and then you have like your like root directory and then your root directory breaks into like multiple other directories. Like for me, I think I have like desktop, downloads, documents, and then random other stuff, and then you keep breaking them down into directories. Like that's a graph in and of itself. Almost like a binary, not exactly a binary tree, but it's definitely a tree. So, yeah, binary tree, I like that too. But yeah, so like more complex graphs can be like a really good example of this is like LinkedIn or any social media. It's like you have X person connected to X person, and usually these are directed, which means that like just like showing the direction, right? You can have like a graph where it's undirected like that. So that means like these two are disconnected, but if you have directed, it means like you can only go from this node to this node and not this node backwards. So like take Instagram, for example, like I could follow like a celebrity, but obviously the celebrity won't follow me back. Kind of bogus, but no. But yeah. So that's like the essence of like graphs. You probably encountered them a lot. They're pretty, I would say they're conceptually pretty simple to understand, but the algorithms on them are a little more complex. So we could take, for example, I'm just going to abbreviate it as like DFS. So DFS is basically a search algorithm on a graph you apply to a graph, right? So let's say you have like, I don't know, you can make some like random graph. Like something like this, and I'll label like F for finish and S for start. So what DFS does is you pick the next node, and then from there you explore the edges. Or sorry, you explore the node that you just got, like the most recent node. So for example, like let me label these actually so that we can differentiate. Um, that way, like when I'm trying to decide between like tiebreakers or something, I'll pick like the alphabetical order one. So like let's say I start at S, right? I go to A, so that's my next node. And then like I don't like from here I try to go to like A's neighbors. So like let's say since trying to explore everything, I go to B, right? Because this is the next alphabetical one. And then I go to C, right? And then D and then E and then F. This is different as compared to like breadth first search. So like breadth first search would do something like A, and then it'd go like so go A, and then it'd go like B, D, and then it explored these, and then it keep going. But depth first search is more like a line, trying to go as deep as possible. I guess like a really good example of this is also in binary trees. This is kind of a problem I'm gonna talk about today. So like let's say you have like a binary tree. So you're starting obviously right here, right? But depth first search would make it so that you go to this node first, right? Right here. And then you go and explore this node's children, if that makes sense. So like breadth first search would be something where you explore this node and then this node, and then this node's children, and then this node's children. This node's children, and then this node's children. So then you'd be here. And then you explore all of these guys as children, like a layer. Does that make sense? But like depth first search, you'd go like down the line first, and then here, and then propagate back up, and then down the line here. Does that make sense? Or you could go this way. Let me know if you have any questions on this. Just realized my background is blurred on here too. That probably doesn't help. There we go.
I feel like if that's somehow, but yeah, you should like stack when you're doing that.
Exactly. Yeah. So like BFS, you would use like a stack, but like it depends on like the order you pop in and pop out. So like BFS, you'd pop in from the front, or you'd pop from the front. So like say A, B, C, D, E, F, G. So like let me do DFS first because and then I'll compare that to BFS. So like let's say you have a stack. A stack is just like think about it as like a list. But like the only thing you do differently about a stack is that like you you put stuff in and then you can either pop from the front or pop from the back. Usually in a stack you pop from the back. So it's like last in, first out.
Kind of like a bunch of like books, you said, a bunch of like books. You have to
Yeah. So like let's say we got like so first we'll explore A, right? So this is for DFS. We'll put A in here and then we'll pop A off and then we'll put let's just put E and B. I want to go to the left first. and then we'll pop B off, right? And then from here, we go to like C, no, let's go D and C. I want to explore the left subtree first and then go down. And then we'll pop C off, but there's no children. So you can see how like we're going down here, and then we'll go here, and we'll propagate back up. As compared to like DFS would be like I'd put A in, and then I'd put in B, E, and then I'd be like, okay, let me just pop in the front. So then I put B. So I pop B off. So like this is what I'm exploring right now. So I have E and then C, D. But like I still have this E in the front, right? So then I just explore E first. So then I have C, D because I popped E off, and then F, G. And then I just go ahead and explore all of that. I think breadth first search is really good on binary trees for like level order traversal. I don't know if I'm saying that right, but like basically like breadth first search is really easy to output the nodes or the values of the nodes in each level of the binary tree. And similarly, like if this was like, let's say a graph, this would also explore like the levels. So like this could be one level, this could be another level. It basically be very similar to this, but yeah.
For like DFS, like a graph that doesn't have like structure like that, how do you know like, it's like this goes like all the way to the left, all the way to the right, how do you
Yeah.
know like the
Oh.
direction to go from?
Yeah, so I guess like I I guess like it's super easy and like I don't know, cause like
Or I guess is it just like explore all neighbors?
yeah, it's like yeah, but I guess like in problems like something's unlabeled like this. I don't know, we'll have something like that, and then like maybe this graph will connect to here and then here. But like in problems like this, where you're just like exploring a graph, let's say you start here, depth first search means like you try to go like as far in as possible, right? So you'd go here and here and here. And then there's kind of like a situation where you're like stuck between two nodes, which you can explore. You can explore this one or this one. It's purely by which one you append to the stack first and then pop off, or append to the stack last and pop off. So like usually like I know like some problems when you're doing this like just like theoretically they might have a graph that label it with some value and then you pick like a tiebreaker. So like if I was doing depth first search, I'd explore like A first because A is a lower value than B in terms of like that. And then I go here and then there'd be like another tiebreaker here also. But yeah. There's sometimes where like actually let's pretend like A was this was the only edge to A. So like I'd explore A, and but there's nothing there, right? So I come back and then explore B. That's another option too.
Do you have to keep track of like nodes you visited so you don't revisit nodes?
I think with DFS, you don't have to because the stack kind of does it for you. Because you never will go backwards, if that makes sense. So like I should always be going this way. And then my stack here, like I'll have a stack here initialized to this node value. And then this node value, like I'll pop it, this one, this one, this one. And then my stack will have A, B. Like when I'm at this node right here, it should have like A comma B, right? So then it'll explore A, cross A off, and then explore B.
That makes sense.
And then it'll keep going there. But yeah. Okay. Is that I don't know. Do you guys have any questions on like DFS? Specifically DFS. I know like I mentioned DFS. That was just like or breadth first search. That was just kind of to show you that there's two very common graph traversal things or graph traversal algorithms. But like if you want me to run through like maybe like an example graph that you thought of yourself or something, let me know because thinking we might hop into a leak code.
So the linked list is just like a straight thing of nodes.
A linked list? Yeah.
For
Oh yeah. Dude. Well, I should do maybe in the future I'll do like another one. I think like reverse a linked list is like super popular. Like yeah, so a linked list is like it's I think so like you make a class, right? I think in Python they have like classes and stuff. So like you can make a class where each node has like a value. Usually, I don't know, like sometimes this is like a common linked list. Like you have a value, and this value has like a pointer to like the next node with the value. And basically, instead of like a list is sort of like a linked list, but like instead of like the typical list in Python, where it's just like stuff in memory for in like consecutive memory. Um, a linked list is more like you have something in memory that points to something else in memory, if that makes sense. So it's almost it is a graph, in my opinion, because you got nodes, you got edges going to each thing. Does that make sense about linked list?
Because then if you like removes two, he wouldn't point to it anymore, you'd point to three.
Yeah. So like let's actually run through that. So like let's say I wanted to get rid of two, right? All I do is I'd set the pointer from 1 to 3. And then I'd move the pointer from 2 to 3. So then that way I get rid of this entirely. So now there's like a node, but nothing pointing to it. So if I like usually you have a pointer initialized to the first value, like the head of the linked list. So that way if I run through this linked list, I'll never be able to get to 2. So it's like fully removed from that linked list. Does that make sense? Cool. Any other questions or that's a good question. Any other like things I can go over or things that should can help clarify that first search? It's kind of a I don't know, it's kind of like something you gotta like do like a couple of problems with. I'd say it's uh like more not even like computer science problems or not even like coding problems. It's more like create your own graph and then run depth first search on that graph before it's somewhat easier to visualize. Okay. All right. Something before we get into this leak code, I have a couple leak codes, but this one, the next one will kind of go by pretty quickly. And then the second one is actually a stumper. So yeah, I'll try to figure that one out too. But something, what was I gonna say? Oh yeah, yeah. Something so like I mentioned stacks, right? So with depth first search, whatever value you put in to the end of the stack, let's say you have like X values prior to this value you're about to put in this list, and then you pop out, right? You take this, whatever you put in last, you take out. So that's depth first search essentially. That's how you represent it for a computer. But something you can do, like instead of having this physical stack that you keep track of, you can also use recursion, which is basically it keeps a call stack. So like let's go back to this binary tree example. Like I could keep a stack here, or I could literally have a function that let's say goes only through the left of the subtree first. So like let's say notice what I'm gonna have right here. I could have a subtree that literally goes node dot left, and then like I'll call it fun for function, and then I could literally call it again. I could call it fun node dot left or something like that. So this function, and then let's say I call it like let's say I define it right here. It's pretty bad here, but like let's say I define it here, and all it does is call itself, but on the left subtree. Let's erase that. It's just a node dot. I'm like ignoring some base cases right now with recursion and things like that. But like this recursive function will all it'll do is call itself on the left subtree. So like you can imagine if I pass in like let's say this node right here, which I'll call root. If I pass in root here, it'll call the function will call itself on root dot left, which is the left child of root. So it'll go here, and then this will be like the new node that it's looking at right now, and then it'll call itself on the left child of that again. You can imagine it'll just keep going down this way. But like you can see how like in the call stack, what will happen is this function will be called on the root, and then it'll call us up on this and on this. And then once it hits some base case, it'll propagate back up, which is kind of like the stack. So I guess if I label these nodes right here, it'll have like in the stack, it'll have something like fun of 1, fun of 2, and then fun of 3. And so it'll literally have like the function calls, but because it's a stack, right? You would evaluate fun of 3 first, which would be this one. And then the value, maybe like you're recursing and you're passing a value to the next case. So then it'll pass this value up to 2, and it'll pass this value up to 1, and then it'll be does that make sense? Cool. Any questions or like any cases you want me to run through or something like that? This might be more clear on the problem because the problem is the leak code problem is pretty similar to this, except just a little bit more. But if you guys are good, we can hop into this leak code real quick. And I will put this up. Come on, please. Please display HTML code. Yes. Okay. All right. I'm going to give you some time to read this problem, but yeah, there might be a slight confusion on what in order is. And I can explain that too. But yeah, just take a moment to like read it real quick before I get into this. And if you guys have a question about in order, I can also explain that real quickly. Let me know when you guys are done or need more time or anything.
Like left, like print out the entire node, like return the entire node.
Exactly. Yeah. Yeah. So like it's actually real quickly, they don't do a very good job of like describing what in order actually means, which kind of pisses me off. But so like yeah, you have your tree right here. Lyman actually did a really good job of talking about this. Discrete, yeah, as the class. But you go left, propagate all the way down, then you return this node, and then you go this. So like I kind of think about it as like, say I got this red marker, right? I'm going down, and then right here, I return this one, and then right here, I return this one. That's when like I reach the bottom of the node, I return it. If that makes sense. This is kind of how she taught us. And then that one, like right when I like when I'm drawing this and I go underneath the node, that's when I return the node for it. Does that make sense? Cool. Yeah. So then it'd basically be like the left subtree, then the root, and then the right subtree. So like what's the test cases? Like here, let me give one right here. Let's say root equals 2, 3, 2. Let's go null, and then 3. Like what would be the in order of this?
One, and
2, 1. Okay. Yeah, it's pretty close. We can visualize it. So like the root equals 1, and then root dot left, which is the left child, right? That equals 2. Oh, I don't know why I just put that in parentheses. That equals 2, right? Because that's right here. But the right child of root is actually uh equal to null. And then root dot left. This is really confusing, but bear with me for a second. Left equals 3. Does that make sense? So, like, it's weird when you see a binary tree like inputted as a list. But this is basically the first value is always the root, so it's a top parent. The next two are like the children of that parent, if that makes sense. So like this is a left and this is the right, and it always follows that order. And then the next following values will be the next two values, like if I put 3 comma 4 would be the children of 2. Does that make sense? Okay. Let me put that up in comments. Gosh. Uh, yeah, I can't. There we go. Let's put that in comments. And then let's like, so they want us to basically go through this tree and think about how to return the left subtree first, then the root, and then the right subtree. So let's think about like a recursive solution for this, right? So like I guess what first things should you I didn't like this question. I don't like what are like some things that jump out at you that we should probably do first when defining this function? We do. I think a helper function uh would be helpful. Okay, so let's put this helper function in. But even before that, like I guess like we know that we have to output a value. So like what should we do like prior? Like we should have something that keeps track of our output, right? Does that make sense? Oh, sorry, what yeah, exactly. Yeah, so we can call this array res short for result. Um, okay. And then let's go through this helper, right? So this helper, what I'm thinking is we can kind of recurse, kind of like what we did up here, where we went through the left subtree, only the left subtree first. But we can think of like a recursive solution for this, right? So like in order, like I guess like when you're doing an in order solution, what would you do first? Would you go through the right subtree first and then the left subtree, or flip the order around? Exactly, yeah. So let's go through the left subtree first. So let's do like let's call like kind of what I was doing where I was calling like fun on itself, but you could do like I could call helper on itself, right? Um, and then after you go all the way down the left subtree, what do you do after that? You you go backwards, exactly, and you go backwards to just the parent, right? So now this is our time to like since we have this result array right here, this is our time where we want to like put the value in the result array, if that makes sense. So I guess like how would I do that? If I wanted to, oh, by the way, I didn't mention this before, but node.val gets the value of the node. So like let's say like the node.val equals 3. That's how I'd like get the actual integer of it. So like let's say I wanted to append the like res, like to res, I wanted to append the value of the parent. How would I do that with Python?
Like the stack, like
Yeah,
you add each like stack.
exactly. Yeah, exactly. That's perfect.
And then so you take it off the stack.
Mhm.
And then whenever you take something out of the stack, you would add it to
Exactly. Yeah. So like, I guess how would I add it to the result?
dot.
Hmm.
How do you get the node dot value?
Yeah, exactly. I think that's all I need to do. I don't think it's like an actual function. Okay. It's kind of, there we go. And then now now after I've appended the value, what do I want to do next? Because I've already gone through the left subtree. I've already gone to the parent. And now there's one more part that I need to explore, right?
Right.
Exactly. So like how would I do that? Exactly. Nice. Okay. Our last case, and not case, but more so like we want a recursive function to end, right? Oh, I should say we're passing in a node in here. Um, what would be like if something, then I just want to return.
Like if the result is equal to the length of
Close, close. Um, let's think about this. Like, what happens if I straight up I should have mentioned this before, but like these in a binary tree, the leaves, they point to nothing after, right? Because it's the end. So like if I want to check that I've reached the end of a subtree, like how would I know, you know?
the
Exactly. Yeah, yeah. So let's say uh let's let's be like this is a little weird. So like this actually I think in a binary tree this points to something. I think it points to like none. I want to say. I want to say like in binary tree, the constructor makes it point to none already. So we basically want to say like if this is none, right? Then we've reached the bottom of the subtree. That makes sense, right? So another way, it's weird, but like in Python, I think this is why it's a little simple. None is given a value of false. So in this if statement, if we could say like if not node, because node is the value none, right? So if I say if not false, so if true, then I would return. The only case that this base case wouldn't work is if the node is like an actual object. So then I would be saying if not true. As it's like a little Python syntax thingy, but like yeah. Um that seems about right. There's one last thing. Now I've defined this function. I spent so much, hard work on it. What do I got to do to actually make this function work? Or to actually like, implement this function. I want this function to like run on something, right?
helper on
Exactly. Yeah. I don't know how I did caps lock there. It's crazy. Helper, root, and then we can just return the answer, right? Return res. Okay. That's John. Okay. Let's submit this. Bruh. Okay. Did I seriously just miss the button? Okay. Yeah. So I don't know if that makes sense or not. Is this if there are any questions on this, let me know on this code. Maybe we can run. Do you guys want to run through like an example of what exactly is happening here? Or yeah, go ahead. For sure. Okay. Does this question make sense, Ruben?
like
Yeah, no, if you want to run through an example, we can do it on the whiteboard too. I know that I I know this recursive thing. It's it's weird how like there's sometimes where you run like DFS on like an actual like you'll have like a stack or something, like a stack equal to a list, and then you do like stack dot append something and then stack dot pop something. That's like the more
I guess, formal way, but that's what I'd consider iterative DFS, where it's like you use a for loop rather than this recursive way where you actually just let the recursive functions make the stack itself.
So like a benefit.
I think I think for something like this, I the recursive solution is just the easiest to comprehend. Because like you can clearly see like, oh, I'm definitely going to the left subtree and I'll just keep going to the left until nothing happens. And then I'd go to the parent and then I'd go to the right. Whereas like iterative, you just go through like a for loop and then you have to actually like iterative, you'd have to keep track of the stack. But like if you do recursive, the stack keeps track of itself. The stack keeps track of itself. Yeah.
And what is it about, like prefix or not, but
Mm.
like first one, you must change that.
Oh, like pre-order
Pre-order
stuff.
so
I think there is
you
a,
switch over
yeah. Let me pre-order. Ah, dude, pre-order. Oh, not that. Pre-order graph. It's the left
yeah, it's like
and then the right. Oh, I see, I see. Dang. Okay, so then oh, that's what I'm gonna go over later. So you put this first, and then you keep going. Let me actually pull up the pre-order. Pre-order lead code.
like or go down a little bit.
This one? No, this one. Oh, this is someone's solution in C++.
Oh, okay.
Come on. Binary iterative, of course. There's no way. Oh, this. There's definitely like a pre-order traversal somewhere. Problems. Pre-order. No, I don't. Binary pre-order traversal. Let's go. Yeah, I'm just gonna copy paste this code. It should be like the same. Oh, that's in order. Never mind. All right, let's run this, John. Let's run. Okay. It's just like you'll learn this. Are you taking discrete or have you taken discrete
It's
data structures? Okay. Which is now or next semester? This semester? Okay. So yeah, this is just like this is the same thing as like the other thing. It's very similar to DFS, except slightly very similar to the problem we just went over, but it's just like you can see like I literally just moved this thing or I moved this res. Initially we had it like um we had it right here, right? I just moved it up because pre-order is like you append everything on the left. Everything you encounter while you go down the left subtree, you append, and then the right subtree you do next. But yeah, let's go back to this problem, I guess. Let's focus on this one thing. Does it oh gosh. Does this make sense though? Like how we're like recursing downwards. Okay. Okay. Yeah, this is if you guys want to, the recursive solution is pretty easy, but I know there's like actually the recursive solution is like it's fairly like you got to think about it a little bit, but like they do have this follow-up. So if you guys are interested, you could go to this problem, the binary tree in order traversal, and then just do the iterative approach, which is where you'd actually keep track of the stack. But we should definitely move on to this next question that I really want you guys to look at. This one, this one's called surrounded regions. We may or may not get time for this whole thing. I don't know. Depends on how fast we go. But let me know when you guys are done reading this, and if you guys have any like initial I guess ideas or approaches, we can definitely talk about this before we spend the next like 15-20 minutes on it.
This is like order directions around. There's my side.
Yeah, this is a good question. So like it means north, south, east, west. I literally did not point to the right direction when I said that. North, south, east, west. Not the diagonals. So the diagonals don't count. Wait, no, I lied. It has to be surrounded like no, yeah, yeah. The diagonals don't count. That's why in this case, like even though this region right here isn't totally surrounded, right? There's an O here, it still gets converted to X's because the everything like the north, south, east, west of every O is covered by an X or surrounded by an X. This one's a little tricky just because there's like once you get this one thing, then you realize like
Like a depth.
it is, yeah. It does use that. But there's like a clever way to use it, if that makes sense. I guess like an initial hint would be like, oh, let me scroll down so you can see a full example. An initial hint would be like, there's some cases where you actually use depth first search, and some cases where you don't.
Feel like initially I go through until you find and then do that first search from there to like branch out.
That's a good first approach, yeah. So like you're saying like iterate through this list, and then like up we go and oh here, and then we do depth first search and find the region. Yeah, you could do that way. But there's something like really clever. All right, that's a terrible second example. It's just an X. Um, hmm, trying to think of, yeah, let me draw an example actually, because you can make it so that you can totally do depth first search on every O you see, right? You just run depth first search and then like check if that region and then like return maybe you can propagate like a truth value of whether it's like surrounded, if that entire region is surrounded by X's. Let me give you like hopefully another example that'll help. So you have this like giant. Actually, let me just draw a box. So I'm gonna do if I draw an O, that'll mean O. If I don't draw anything, that means X, just so I don't have to write too much. But let's go like this. What would something like this become after it runs that up?
All X.
All X's. Exactly. Um let's do something like like this. What would this become? Yeah, the same thing. And I guess the reason why it stays the same is because we're told like if the region is surrounded by X's, then only we change it to an X. You know what I mean?
Like it's like bottom part, like
Exactly. So yeah, that's a pretty good observation. So like let's keep going with this and let's confirm like what you're saying. So like let's do something like O O O O O O. Yeah, let's do something like this. What would this become?
Yeah, it actually stayed the same.
So we need to check the border and then from there do DFS and
Yeah.
modify.
Yeah. So like I guess like something that wasn't explicitly stated in this is like it has to be surround. I mean, it was sort of explicitly stated, like it has to be surrounded by X's everywhere, right? But like, what do you do in the case where it's just on the edge, right? There's not an X, so technically, it actually doesn't change it. So like, you would notice like as soon as I take away this O, this is surrounded by X's, right? So then this whole board would be an X, like just filled with X's. But as soon as I do some O that attaches a region of O's to the border, that's when like that region will stay. So we only need to run DFS on the border O's and not actually anything else. Yeah, so really clever. And there's something like even more clever, like when you do the DFS, you do like another little thing. So that way it like saves like the regions that you actually let's do this right now. So like let's erase this out. So like you can tell right here, right? This region is not surrounded by O's. I mean X's, because the border, right? It's connected to the border. But this one is. So like how, let's say you're iterating through, you're running DFS. How would you when you try to change the values to X's, how would you know which region to change? Because you run DFS only on this one, right? Because this one's only border.
So you like check the surrounding, right?
Uh-huh.
And then like check if it's no. And then if so, recursively go on that one and change it.
Change it like I guess like what would you change this?
So like to X, right?
Well,
Like you
this
first,
one?
yeah, like so you change that first one to an X and then like check its neighbors. And if they're like, let's say the top one is, or not X, like the top one's a no, so you like go there, do it recursively and check its neighbors.
Okay. But like, let's say like I run my DFS and everything, right? I want to differentiate between these two regions, but I can't right now because they're both the same values, right? They both have O's in them. So like, how would I know which region I ran DFS on and which one I didn't?
Are you modifying it like in place?
Yeah. So like, well, I guess like what would you do? You ran DFS on this, right? Because it's on the border.
Yeah.
What would you do to this region?
Like take the X or change like the value. Is that what you
Yeah, you can do that. That works. So like, I guess give me an example. Just there's something out there.
like 2, 4, like what do you mean like the coordinate or
No, like, yeah, you said change the array value. You can do whatever you want. Like literally anything.
just like set it to an X, right? Or are you saying like,
Don't set it to an X. X is already used.
oh, you mean like set it to something else?
Yeah, let's set it to something else.
Okay. So just like, hey,
Hey, exactly. So like, because Ruben, you said like, if it's on the border, I don't change those regions, right? So that's why we run DFS on these ones. This one right here and not this one. Because we know this region will stay. Because there's no X's surrounding this entire region because it's on the border. So if I run DFS and I'm like, okay, well, I know this region already, I know this region is good, like it's gonna stay. Let's just change it to A. And then when I like finish my DFSs and then I run and change the O's to X's, I'll just change these to X's. And then I'll maybe do another iteration through and change the A's back to O's or something like that.
could you also like make like a set and like store all the coordinates, or is that just like
You could. You could, yeah.
see?
Yeah, you could make a set like this, and then you put the coordinates in. And if you're like, if IJ is not in the set, then or if IJ in set, leave it as O. Or if IJ not in set, then change to X or something like that. So like in that case, all these A's would be in the set. The coordinates of these A's would be in the set. Coordinates of these O's would not be in there. So your check would be that. I would say that the reason why modifying this is so nice is because then you don't have to take care, you don't have this like extra space complexity right here, which worst case is n or n times m if the whole thing is O's. So yeah.
So you're like setting, so you change everything that's connected to the border.
Yeah.
A, and then change everything else that's not an A.
Exactly. And then the final thing, just because we need to output it with those, is we'll change these A's back then. And then we'll get going with that. Sound like a good plan? You guys want to help me code this up? This will be a this one's a little tricky. I was practicing this one if here, let me actually, it's like Splunk. This one right here. I was doing an interview with Splunk, and this was their all-time high, 20% frequency for this question, which is crazy. By the way, this was the questions they asked me were nothing close to this hard. They asked me not valid anagrams, group anagrams. That's what they asked me. So yeah. Yeah. I did not know how to solve that, bro. But yeah, let's go through this. So I'm just gonna set like two variables. These are gonna be the dimensions of the board, okay? So I'm just gonna set like rows to the len board, and then the len of like the columns would be board of 0, right? Does that make sense so far? No, it won't. Yeah, so this would be like let's say like rows rows would be initialized to like some value n, and then columns would be m. But this allows us to like it allows us to like make the code a little bit cleaner. So next we have to, just like in the last one where we had a helper, right? We should definitely have another helper that basically just does the DFS for us, if that makes sense. So let's plug in a row and a column into that. And this will be like, this will only happen if we run into a like an O at the border. That's when we'll call this DFS. Okay. So right, I guess like this base case is actually kind of crazy, I think. So we need to check our base case needs to be, is it at the border? If it's at the border, is it not at the border? If it's not at the border, then you just don't do anything, right? You just want to return. But if it is at the border, then you want to run DFS on everything. Okay. So let's do that. So if row less than 0, or this is to oh man, this is to check out of bounds, I'm pretty sure. Or row equals rows. This is gonna be a long one. Or column. Actually, types out the word. Okay, columns. Or word of row column. Oh, column does not equal the letter O. Oh, oh. Long base case. Trust me on this. Checking if it's out of bounds, right? Or we're checking if it's like, because len does like plus minus, like len will get you an index 1 too far, right? So if like a list is len 10, it's actually indexable from 0 to 9. But you can't, so like basically we're saying if the value's greater than the actual like indexable region, then you just want to return, right? Else, now we can just do like let's do that change, right? We wanted to change it to, so like it'll return, so that's our base case, but like let's say we want to change it to you said A, right? So let's change it to A. So now we change this O to an A. So I guess in our example here, we still have these two O's, but we have this A right here, right? Does that make sense? Now, like, we need to call this function again, right? But
we need to know like where to call it. So like, how would you guys? I'll give you a hint. We need to call it 4 times, but what would you pass in every time? I'm just gonna put like row column in each one. But like we have to modify row column to check all 4 directions, right? So how would you guys do that? You guys, Ruben?
We're like trying to like make a graph. Make like
I mean, sort of. You can think about it that way. We're trying to like, so like we find this what was originally an O, right? And it's at the edge of the graph. So once we found this O, now we want to do DFS, but DFS isn't necessarily always on graphs. I should have specified that. It can be on like a matrix or like anything that's sort of connected to one another, right? So in this, oh, sorry, go ahead.
so is it like it's like
Exactly, yeah. Ignore the diagonals for now. But like you can visualize like this region, like you can see like this cell is sort of connected to this because they're both O's.
like a block of
Exactly. Yeah, exactly. Yeah. So like we want to check the 4 things, right? So like we want to check this region, this region, this region, and this region, potentially, if those are O's.
so like row plus one,
Uh-huh.
row minus one column, and row column plus one, and row.
Yeah, yeah, exactly. Dude, nice. That's it. -1, and then you said row column +1, right? And row column -1. All right. That was pretty good to me. Base case will take care of everything. So now this is where we need to like just straight up go through the entire matrix and just call the helper function on the O's that are on the very edge, right? So let's go like for row in range, oh, I guess row and rows for column in range columns. I can't scroll down. Column and columns. If now here's where we check, like we need to know whether to call helper or not. So we need to basically check like is this O at the border, right? So I'm gonna do the first part right now. Row, if border row, border column, and dude, these parentheses are really messing with me, equals O, right? And we need something else, right? So how would we check if it's at the border? There's something special about the row or the column value that we need to check.
Or if like the one that's like one of the ones that's getting to
Close enough. I think it's pretty close. But like, let's run through this real quick. So let's say, I guess in the indexable region, this is 0, 1, 2, 3, 4, right? 4, 0, 1, 2, 3, 3. This is 4, 3, 4. Whoops. And then 0, 0. This is 3, 0. And this is 0, 4. So these are this whole row, right? This whole column, this whole row, and this whole column, that's the border, right? There's something special about the values, the indice values that
like the column is 0, the row is like the equal to like the length of like the board,
yeah. Yeah.
and then for the row is 0.
Exactly. Yeah. So we need to just check like, does the row or the column equal a certain value, right? So let's do that. And let's say like row in this is gonna be really complex. Let's do I'm just gonna like row in, we'll just check this, right? Do rows -1. Or column and this helps me save like another like couple cases, you know, like in terms of like just like typing it out. Because God, dude, that's like a long check right there, right? Yeah, let me move this out. So I think that's all you need to do. Because what I'm saying is like if it equals O, so that's one case, and then in parentheses, I'm evaluating this. If either the row is zero or this, if it's either this zero row or this like len of rows minus one, right? This final row, or it's this column, this final column, or the zero column. So I just need one of those conditions to be true. Then all I need to do is run helper of a pass an R comma C. And that will change it to an O. Let me actually, can I print? Let me print board just because like we spent a lot of time on this right now, you know. Don't want this to and don't want this to oh right here. Yeah, good catch. Okay. Well, it should be wrong, right? But you can see, right? We're changing these A's, the O's to an A now. And in this case, case one, you only need one A because it's this one right here, right? So we're running the algorithm correctly. And so now all we need to do is do this in another for loop again, right? Now we need to change everything that's not an A to an to an X. If board of X, then now we change this to an X, right? Just to an X, and then the last one, right? Oh, and then now we got to change our A's back, right? So goes A back to an O. Now let's run this. Sorry, if it's an O, hmm. I'm not sure why it's not changing it back. Output, it still has an A. Hmm. Yours? Yeah, that is kind of weird. Let me see if I can some. Okay.
You put a zero instead of.
Did I? Oh, dude, you could be totally right. That was wild. I did that. Just copying and pasting like that. No, damn. That'd been so nice. Capture O, then change it to an X. So it might be something. It might be something. Oh, you're totally right. Good catch. Good catch. Ruben, you're god tier for that. Good catch. Oh my God. I thought I got it. Fuck. Okay. Wait. Lennon board zero. If these there's some syntax thing right here, right? Let's put this. Uh-huh.
Check like that. If it's A, check.
Oh, we're gonna be going over everything. Yeah, I think we should be able to do that. Yeah, you're right. You're right. Uh, there. We can delete that. I just want to check if this passes on the other two, then it should be fine. Yeah. Okay. So it's still that one problem somewhere. Okay. If row is greater than zero, dude, this is what happened last time. I swear to God, I was like missing one thing. If it equals O, change it to an X. If it equals A, column. Okay, let's start from the top. Rows, columns, line of board 0, helper, row less than 0, column less than 0, equal to rows, or column equal to columns, or the board doesn't equal 0, you just want to return, else just change it to some letter A. Okay, +1, -1, +1, -1. That looks fine to me. For range in rows, columns, this is our global variables right here. If it's in R, oh, which that's out, right? Okay.
Double, like square brackets and like line 21 at the far right.
Far right. Oh, shoot. Wait. Yeah, that's totally right. Dude, Ruben, you got a good eye. Dude. Man, good catches. Look at that, bro. I wouldn't have been able to pass that if it weren't for you. Good stuff. You should be proud of yourself, dude. Good catches. Yeah, no problem. Yeah. And that was also way to condense that too. That double for loop thing that yeah, I know it's like if we do like big O of n, right? We'd be doing 2 iterations throughout the matrix. So it'd be m times n or 2 times m times n. But this way, like something that I was asked a lot in my interview was like, how would I optimize something, right? And even though like big O, like it's still the same big O time for this function, it's m times n, worst case. We just like Nick just put the suggestion out that now it's not 2 times m times n, it's just m times n is 4.
Might not make like big stuff, but it's like
Yeah.
a huge amount of data. I mean, it's like it's rather like it's cut it in half.
Yeah, exactly. Yeah, cool. Any questions, any comments, concerns about this problem? It's a fun one. Definitely, you definitely need that trick that you saw, Ruben, about the O's being on the border. Otherwise, this problem's literally impossible. I think I was staring at it for quite a while trying to figure that out. But yeah, any questions on this? Otherwise, I'll show you guys one problem, but we won't go over it. This is something I got on Google when I interviewed with them, so I just want to show you guys. Okay. No questions, comments, anything? No? All right. Let me show you this one and then we can kind of talk about this one. But yeah, let me know when you read this. And this is kind of one where like maybe if you want to pull it up on your own or something, keep like a tab and then like solve it on your own. I don't think this is like a leak code. Yeah, let me actually make it bigger so that way you guys can see it better. But I don't think this might be some leak code somewhere. I haven't seen it before, but like in leak code particularly, but
This is all like a DFS.
yeah.
It's like
Yeah, Dijkstra's is a little bit different. So Dijkstra's is more of like yeah, Dijkstra's is like how we were talking about like graphs and stuff? We didn't actually like assign a weight to a graph or like a weight to an edge. So like Dijkstra's, what that does is it traverses, I think basically the entire graph, and it gives you like the value, like the shortest weight of the shortest like value for the path from like X vertice to Y vertice or something like that. So like you could have like 10 nodes and each edge has like a different value, like a cost, let's say. And Dijkstra's would give you like the lowest cost to get from like node 1 to node 9.
a bunch of like planets.
Yeah. Oh, dude, that's a great one. But yeah, I can talk about Dijkstra's. Well, it's a little bit different because there's no cost in this thing. There's only like an option where it's like one you can take. I think one is you can take it. Like consider you have a car, right? One is like, oh, it's a road, so you can drive on it, but 0 is like it's not a road, so you can't drive on it. And you're just trying to see like, oh, is there like can I like drive from this top left all the way to the 9 right here? And in this case there is because you can drive down, go right, go up, and then 9. Sorry there. So like you can see how like this is like a depth first search more so, right? Because like you see how like I'm like searching in and I keep going and I just keep digging deeper and deeper like depth first search does. So yeah, this is more so a depth first search one. I know like it's weird. I think Netflix might have asked a Dijkstra's question. And it was like implement Dijkstra's, which is actually kind of hard. Low key. Yeah. Like thing, but yeah. I guess yeah. You guys should I don't know, we're kind of taking a while. I didn't expect to take this long, but I don't think we will solve it, but the initial approach is depth first search. So that's I'm gonna put that out there.
Recursively. Go through all of it. And it's until I guess you need to keep track of like where you've already visited.
Yeah. This is something I made a mistake on this too. I recurse. So like what Nick's saying is like you just every time you see one, you just check off four, right? Kind of what we did in this last case where we checked off four cases. But I didn't keep track of like whether I saw something or not. So my recursive solution actually would have gone infinitely. And that's something they pointed out to me. Probably why I didn't get it.
Like, two it's like,
Yeah. Yeah. Change it to true. That's what I did too. I just made yeah. Something you can do. Actually, you know what? You guys should solve this on your own. I think you guys got this. It's definitely a lot easier than this one for sure. But yeah, just search this up on your computer or something. If you want me to share this with you guys on Discord, and then you guys can go ahead and solve this. Don't scroll down though, because the answer is down there. But yeah, I should have Googled this to be honest, prior to my interview. I didn't prepare. What's to really create a problem though? Google is if you guys don't know, Google really likes their graph algorithms. I got two graph questions and one really easy one. Yeah, but the graph questions were the second graph question I got was hard. It was like actually hard.
It's like
Yeah.
tracks.
Dude.
So you have a nice structure.
Graph. Oh yeah, 100%.
I don't know.
Yeah. I think Google likes graphs just because I feel like it's one of the harder things to understand. And so if you get an applicant that really understands graph, I feel like
They really grind. Like,
yeah, they probably like you can assume they understand like arrays or something because graphs are just harder to understand algorithms on than like something like an array. But yeah, okay. That's all I got for you guys. You guys got anything for me? Breadth first search? There's like level. This one, you can do this on your own if you want. Level order traversal or something. Leak code. Come on. Give me the question, bro. Oh my God. They always do this to me.
but it's like an array, like first level, the second level, and all the numbers.
Yeah. This is like breadth first. Let's go. Oh, I got it. Problems. I can. There we go. Search that. Come on, give it to me. Level order traversal right here. This problem, if you also want to learn how like when you use breadth first search, so like, damn, I got the solution right here. I gotta like reset this so that way I can like solve these again on my own. But like you can see like breadth first search would go like it explore three first, right? And then it explore all the children of three. So it'd be 9 and 20. And then explore all the children of 9 and 20. So which in this case would be 15 and 7. It unlike depth first search, it wouldn't do like 9, then 3, then 20, then 15. or sorry, you wouldn't do like 9, 3, 15, 27. Like that's not what breadth first search would do. Breadth first search would go like level by level. And so in this case, you see how they want the output to be that way, right? So you just do breadth first search, and like we talked about in the beginning, you have a stack, right? And you just pop from the beginning rather than the end. But yeah, this one I think there's a really good. I would if I were you, I would go to a little easier breadth first search one. I think it's medium. What's the percentage? 66. Okay, so it's not that bad. But like really good site. Neat obviously, but I think Neat has a solution on this that I would watch because it's pretty like once you listen to like one solution from Neat with one algorithm, then I feel like it's easy to take that and go to like a harder one and try on your own.
Did this one like 5 times, just like.
Yeah. Oh, yeah. Yeah, exactly. Yeah. Yeah, because like you want to pop like in this case, this level you want to pop twice from the stack from the front. In this case, like let's say there were 4 children, then you'd want to pop 4 times. Yeah. Yeah. Okay, guys. Enough of that. Any other questions before we conclude? No? You got the stuff like
Yeah.
the tabs and everything. This one. Nice. Yeah, solve it on your own. I think VS Code would be use VS Code to solve this one. Just like make your own tests and stuff. Solve that. Yeah. Should be it. Thank you guys for coming. I appreciate it. I know it's like a small turnout, but yeah. Hey, it's like UI UC, that's like the Harvard of CS in the Midwest. Like really? You apply there? Oh, really? Oh, so yeah. No, they're hella competitive. But like to get into like their competitive programming clubs and stuff like that, you gotta like not audition, what is it, compete. You gotta like actually do like tests and stuff. But like for Iowa, since we're not that intense for CS yet, showing up is like more than enough to deter people. So yeah, cool. Cool. Yeah. Thank you for thank you for coming. Thank you for helping me solve that problem. Could not see those little syntax stuff, dude. You got a good eye. I'll see you guys later though.